Okay. Thank you very much for having me. It's my first time at CppCon. I'm having a really great time. I hope my talk will be worth your while as well. So I'm Tobias Fuchs. I'm from Munich, Germany, from a small research team called the M&M team, which is for Munich Network Management. But actually we're system programmers, so if it has a cable sticking out or a core, then the chances are there's someone in our chair programming it. So today I'm specifically talking about supercomputers. So this is from a press release picture by IBM. I like it a lot. This is a photograph when computing was a gentleman's sport. Actually, it was a ladies' sport because operators actually were women. Those were the fine days, and nowadays they look like this. So it's not a gentleman's sport anymore. Actually, the reason why it is not, because we are in the post-Moore era. This is no news to you. So that is to say, in the good old days, you could just wait for a single core to get more efficient. Then we had to add more cores, and we had to add sockets. Then we had to add PCI Express interconnects. And then we had to get really, really weird. So nowadays, specifically when it's about data access, so accessing data from one core in any other memory domain in topology, it's pretty much like moving IKEA furniture with 4096 of your best friends. So why is that? So why am I picking the IKEA example? Well, IKEA furniture is made to be assembled, but not exactly to be disassembled and reassembled again. And this is also true for some of our data structures. So for you will find the corresponding real-world situation in this drawing. So we have narrow hallways, that is to say, well, you can move one couch from one room to another. But if it's like 4 wardrooms, you might want to schedule that a bit. Then you have areas where you don't want to, say, drag your bed through because there is stuff you couldn't validate, like Mom's China. The really far, bulky interconnects are pretty expensive in terms of latency and throughput. And sometimes you have, say, specialists that are really, really good at exactly one job, but not exactly easy to communicate with. So for a real-world example, when it's about decomposing and recomposing, it should stop playing, but it doesn't. Hello? Here we go. Yes. It kind of doesn't want to, but all you in the room know what a multigrid simulation looks like, or multigrid decomposition looks like. And all of you know, of course, what a standstill is. And so in this example, a 5-point standstill, where for every cell, so every cell here in the darker yellow shade has a specific weight, and its neighbor cells, the north, south, west, and east, also have weights, and in every iteration, you just go through all this data, apply your standstill, so center field times 0.6 plus 0.1 north, 0.1 south, and so on. But the problem is, of course, when you get in the neighbor regions, because then, as you all know, you have remote access suddenly because you need a neighbor field that is located at another process. And what we do is, well, we copy the whole range into one chunk, so we pack it into one contiguous chunk of memory. We transport it to the process that needs this neighbor cell, and from then on, we don't have remote access, and then we access this neighbor region because we have it in the process local memory. So the interesting part about this, and this is where we get to the actual topic of this talk, is the index spaces we have. So we already have definitely 2 index spaces for each process. Then we have another one for the Halo cell. And this is just one of those. So for a multigrid simulation, you would have an arbitrary amount of decompositions of ranges. And calculating those indices by hand is really cumbersome and also quite error-prone. So we can pretty much put the optimization techniques we have for data access into 3 main categories. One is to reduce the number of remote accesses. that is, as we just saw, the packing of strided data into contiguous chunks. We can improve the surface to volume ratio, so to reduce the border, the boundary of single blocks. And of course, we can reduce the access distance, which is put in the more general term, improving locality. So putting the executing code to the data it needs to execute. And we have locality on every, pretty much in every level of our machine hierarchy. We all know it from cache optimization, but it's also true for remote access across an MPI interconnect, for example. So we have a library called Dash, which is a pure C++ implementation of a partition global address space scheme. That is to say, we take, say, for example, an array. This 40 is just symbolic. Just assume that's a really, really big number. So it's a huge array that couldn't possibly fit into a memory of a single compute node. And we distribute it as we call it, units. So a unit, it could be, so when you're an MPI user, then a unit corresponds to an MPI process. So while a specific unit is pinned to a specific process, but it can occupy a larger amount of the machine hierarchy. Like, for example, in this case, we have 1 unit per socket, and 1 unit per, those are mixed, so C on phi's. And we can distribute an array like that. And the interesting thing is, well, when you know PGAS, that's no news to you, there's, this is a global address space, so there's, every element has a global pointer, in our case addressable by its segment ID, unit, and local offset. So every array instance would have its own segment. Within this segment, every unit has its partition and a local offset. So you can have, any unit can access, so any process can access any element in this array. You can do it with the regular subscript operators. So you would have an implicit local or remote access. So like in this case, unit 2 would access indices 27 and 35. One would be local implicitly, and the other one would be remote. This isn't too efficient because you always have this indirection of index calculations. So it's perhaps better to have an explicit local access. So that's what we do. You have the local qualifier. And this would reduce the index or iteration space to the local part in memory of this process. As you see to the top left, there is the second argument to the constructor of the array is in this case dash block. That is pretty much the partitioning scheme. So blocked is, this vocabulary is ancient. And blocked pretty much means you have an even partitioning of the memory space into the number of units. And this is all fine and dandy. But we are in C++, so we have a dash array, and it works just nicely as it is. But so how would a dash for each look like? So a stats for each equivalent on the global array. Well, in this case, we have, for example, for each from array begin to end, so over the whole array, and the implementation is actually trivial. As every unit executes the stit for each on its local range. Now, is it actually that trivial? Because we are already violating STL semantics here, because standard for each requires that the unary operator is executed in sequence, so one after another in every element, as opposed to transform. So when you call, for example, the transform, and there is no guarantee of order on which element index the operation will be performed. So we already deviate from that. That dash for each guarantees a sequential execution in local memory space. Yes?
So in that example on the left, where you dash for each, is that distributed across all of the?
Exactly, it is.
Okay. And on the right, that's not distributed?
It is. That would be the implementation. How you would, overly simplified implementation of a dash for each would look like this. So a dash for each translates to a stit for each on the local memory. And this is a classic CMD, single instruction, multiple data. So every unit executes exactly the same code. So this seems pretty trivial. There is no index calculation indirection involved whatsoever. What if we? Oh yeah, I forgot about that. So we have for the regular dash for each, we have one barrier at the end. So it would only return when it has completed on every unit. If you do not want that, We have async and no wait. We try to stick to the STL equivalence here, but this is still work in progress. But eliminating the last barriers wouldn't be not a problem. There's one way to do it is execution policies or any other kind of policy just to tell the algorithm that there shouldn't be a barrier at the end, so we don't have any communication at all. So the union operator is applied on every local element, and there is no need to communicate between processes apart from the barrier. So it gets a bit tricky when it's not on the whole array, but only on the subrange of the global array. So in this example, units 1 and 0 and 3 wouldn't be affected or involved in this dash for each call at all, and unit 1 and 2 only for a specific subrange. So the problem is that we have two index ranges, so to say. So if there's a global one, it is from, in this case, 0 to 40 exclusive, and a local one, and it's not quite clear what it looks like in this case. So of course, it's, so from just looking at it, you can tell that the affected local index range of unit 1 would be 2 to 10, and for unit 2 it would be 0 to 8. And the way we solve this, to calculate this in a more general way, we use view expressions that look like this, so to the bottom right. So in this case, you know perhaps this syntax from Eric Niebuhr's range v3. I can recommend it dearly. And it's pretty much the starting point of our work in this case. So we take the array. The pipe operator has the same semantics as you would know from your POSIX shell. We take a subrange of the global array from 12 to 828. So this is in the global index space, and from this, we would like to have the local part. And well, I already mentioned range v3. So yes, we do not use range v3. We also do not extend it. But not because we do not like it, but just because we have some specific requirements. And I'm not too sure they can be expressed in range v3. I would like it to do so. So if you do not know range v3 already, this is pretty much where we got our syntax from and the semantics of our operations. So I can recommend it very much. There's also a really good talk, I think a keynote even by Eric Niebuhr on that. So our domain-specific needs. So we have a mental model of mapping domains or mapping sets. That is unsurprising. So we have a domain, and mapping transports it to an image. Some elements are mapped and some are not. This is implicitly already included in range v3, but we need to extend that quite a bit. So to just visualize what is happening in this array sub-local, we have the global array. We call the global subrange on it. So from in the global index space from 12 to 28. From this, we take the local part. So this is for unit 2. And you can take the index space from that. This isn't, well, this you could just take it as an enumeration, but it's a bit more like that. Because you can transport it back to the global index space, and then you get the global indices from that. You don't have to, so there's no need to query or interact with those indices. But there are situations where you really have to. For example, let's take the basic std copy. So we already have the dash for each. Now it's about dash copy. So we copy a subrange of one array to the subrange of another array. And for the sake of simplicity, we assume that both arrays target a destination and source are both partitioned and aligned in the same way. So this makes things easier, but still not trivial. So in this case, we have a subrange that is in array A, located at unit 0 and 1, and in array B at 1 and 2. And of course, we do not want to copy those elements, this range element-wise. And this would actually work. You can call standup for each on the dash array, and or a standard copy on the dash array, and it would work. The global pointer semantics are absolutely compatible with STL, as well as all our containers are. But of course, the STL has no model of actual data distribution, because that's the whole idea of it, right? So we try to do with iterators, and they should do all of that. So we want to copy in contiguous chunks, as we saw before. And in this case, it means the first subrange, it has to be an intersection, of course, from the available index range on source and target units, so you don't copy the whole local range, you have to repartition it to the destination range. And we do that for all of those ranges. And this already is really, it's, I would say, the opposite of fun when you have to calculate or implement dash copy in a generic way. So it always has the optimal distribution and communication strategy for any kind of distribution in an array. And this is really simple because most of you know you can also distribute the elements block cyclic. You could use an irregular distribution scheme. So it's really cumbersome just to get all the destination and source indices right. So what we can do with views to help that is, in this case, we take the subrange, we take the local part of that, and we take the blocks of that. So a block is, in this case, a block is a contiguous chunk of memory. But it's just, in this example, every unit has one block in this array. It could be several. And you also have this in the destination range. And then it's way easier to just have an algebra of those ranges. Because building an intersection is rather trivial as soon as you have this kind of interface. So the important part to take from this is, well, we actually do not. It's not about accessing every element in the range. It is important to have this right and performant. But the actual most common use case is that you just take those subranges of contiguous chunks, and you're most of the time you're only interested in the first and last index in local or global index space of this range. So this is one difference to existing range implementations. We are the key feature of our whole approach is the intermappings between the single view operations. So you can always go back and forth between them. As you saw before, you can project an index to a local range, to a global range, and back again, and so forth. And you never lose this state. So as a motivating example, to the right, you see the original implementation of one of several specializations of the algorithm local subrange. So that is what we saw before. We take global subrange, and from this the local part, and this is one implementation we had before we had views. And now it looks like this. This is, of course, this is general. This works for anything. So in formal terms, I try to put it as few mathy stuff in this talk as possible. So in formal terms, it works for any n-dimensional rectangle. And this includes, of course, one-dimensional rectangles, which are ranges. And there is, I can actually demonstrate this real quick. So, there you go. I don't know how much to take. 4. Okay, so we have an array here. And in the whole talk, for all demonstrations, I do the interpretation of the numbers on the screen are always the same. The colors indicate the unit. Coloring is simple. The first, the number before the decimal point is the unit ID, and after the decimal point there is the local index. So we have, for example, 0.0.1, etc. And you see this is not block. This is block cyclic. So the array is distributed in the fashion that there is 2 units, 2 elements assigned to a unit, and then to the next, like distributing a deck of cards. So we take the global subrange of that. We show the blocks of this local subrange. So those are the contiguous chunks in every space. Then we take the local part from that. And this looks different. So this is for unit 0, 1, and 2. And then we take the local blocks from that. And as you see, when I have a global subrange and take the blocks from that, this restriction in the global subrange also applies to the local one. So the first block, so in the last line, we have a complete block from local index 2 to 3, and the first is incomplete because the local index 0 is missing because we subspaced that in the global range. And then we can copy that. So in this case, I copy to the global index range 2 to 9, which is the target index range 2 including NI8. That sounds surprising. Those are the affected blocks in the target range, and this is the outcome. So in the last 3 lines, you see the result of the modified array at every unit, and before you see the affected blocks and elements within them. Now this is pretty much the example on the slides before, just a bit more elaborate and for a more complicated configuration. And I'll get back. There we go. Well, so this is nice. This is a nice gadget. It's not nearly enough to convince users to actually use it. We have really, let's say, traditional users that are really hard to convince to even switch away from Fortran. I don't know if there are Fortran programmers in the room. I totally see its advantages, but it's really hard to argue with Fortran programmers when it's about modern C++ because they usually don't know it. And so the only and best way, reasonably, to convince them is using benchmarks. So let's just run the code on the right against the code on the left. And so this is not a lab environment, so I don't expect absolutely clean, reproducible results. Right. Let's see what we get. So this is giga updates per second. A measure you probably know pretty well. That is to say, a higher is better. So view GUPS is the giga updates per second on a random. So we pick a subrange of the array at random, but we make sure that they are the same for both variants. So for the algorithm variant, the lengthy one to the right, and the view variant, the short one to the left. And we see we get drastic speed up. So it went even better a bit. So I have one run in our lab, and yes. I'll just minimize, I guess. Here we go. And it looks like, yes. It looks like this. So we get up this is with GCC 5.4, and it's a speed up of 6.2. So for those in the HPC domain, this is probably not impressive enough because, well, speed up is always a comparison of an absolute performance of one against the absolute performance of the other. So perhaps the original implementation was just really bad. No, actually it wasn't. So we had the algorithm variant against reference implementations for UPC++, etc. And we were pretty much on par. So it's a reasonable comparison. So where did we get this 6-point-something speed up from? Well, for the same reason that Blaze high-performance math library is high-performant, and for the same reason that views and ranges as proposed by Eric Niebuhr are performant. Because we let the compiler do that. That is to say, when you compose, so when you pipe those view operators in a chain, what you actually do is you configure an arithmetic expression, most of it at compile time. So the whole thing is evaluated at compile time. Then what the compiler sees is the arithmetic expression within every single component of the view chain. Like, for example, sub 1 would mean that every index put into this range would be incremented by 1. And if you put this in a chain, what the compiler sees is an arithmetic expression that can even be constant folded. So it's lots of const expressions and expression templates and every trick in the book. But actually, this wasn't actually the goal overall. My goal was to have a portable, convenient way to express those domain mappings. And what I got was a drastic speedup just because I generalized it in a way that can be understood by a compiler. Now this is one-dimensional. So yeah, it's useful, but it's the two-dimensional case or higher dimensional cases are more important. So first, this is an overview of the typical of the view operations we have. So some of those you already saw. Of course, you have begin and end, size, rank. Offsets and extents is unsurprisingly an n-dimensional standard array of the offsets and of the region, so to say, you have in the view. Domain and origin, so domain would map the view back to its domain, so back where it came from. And origin is, well, you have an array, sub, local, then the origin is the array. So origin is just where the data actually is coming from, and the actual owner of the data. Views don't own anything; they're just all they own is the parameters you pass in the constructor. And that's one thing that is not evident. This is pattern. What is a pattern? Well, the pattern is the static distribution of data. So when you distribute a dash matrix, for example, what you configure the domain decomposition as a static mapping. That is a mapping that is configured with constructor and never ever changes. And it has three stages. So first you have the global canonical domain. Then it's partitioned into blocks. Those blocks are mapped to processors. So unit 1 would get this block, and unit 2 would get this block. And once you have this assignment, you get the local memory layout. So in this case, unit 0, the red one, it has the first two blocks are 0, 1, 8, 9, 6, 7, 13, 15, etc. This is called a tiled distribution. That's also block distribution, where the index will just go in the canonical way. And what we do is the pattern concept in Dash, which will be refined a bit in the next month. It has categories, so properties in exactly those categories, like you would know from iterator categories. So you could, at compile time, interrogate a pattern if it's actually possible to have an imbalanced pattern, imbalanced distribution. So for example, when we just take the mapping between all of those possible index sets, because a block index, of course, is an index domain. You have a local index domain, you have a partitioning index domain. This is what a pattern does, but it's static. It will always exactly do this mapping for exactly this, those extents of, in this case, a matrix. When you just take some properties in the mapping category, this is not this just for motivation that it gets really nasty. So those are already existing definitions of partitioning properties, and we just implemented them in Dash and named them according to the original paper that have been proposed. So the neighbor partitioning would, for example, say that there is no adjacent block with the same owner. Balanced would include that every unit has exactly the same number of blocks, and diagonal would use the k-diagonal to map it. So of course we have several pattern types, and all of those are implementing different semantics, but it's absolutely it would be overwhelming for users just to learn our API inside out. Also, we add a lot of new features and new partitioning traits. So what we provide is just a helper, a compile time called make pattern. You pass it the properties of the distribution you would like to have. And those are easy to communicate. There aren't too much. It fits on a nice slide of paper, and you can just learn them and understand them. You put all the properties in you want. Every property you don't specify is a degree of freedom, and it would give return one of the possible pattern types. What we also do is we deliver a visualization tool. So it's a command line tool. You just type the domain decomposition you have or you intend to use, and it would render an SVG, and you could just see what it does, and this is what it would look like. Now back to iteration spaces. We first saw that within a single block, you pretty much jump between rows and columns, but why don't we just use the regular canonical iteration? So this we do that. So when you just use array begin end, it would exactly iterate in this fashion. So you could use standard copy on a dash matrix, even if it's multidimensional. This pretty much only exists in your head. You can still traverse all the elements in their canonical way. Once you take the actual distribution into account, things get a bit more nasty. So we have actually two iteration orders. The global one, the canonical one, that is also visible to for example, the standard algorithms, and the local ones. So this would be, on the left, the canonical order that you get when you use standard for each, for example, on a matrix, and you have the local iteration order in every unit. So why don't we just throw away the canonical iteration order? Because, well, who would actually use a STIT algorithm on it? And why don't we just only propagate the local one? So we always have iteration order the same as storage order. Well, that would, of course, work, but it's not portable at all. Because when you change the distribution, you would also have to change your whole algorithm, because it now has a totally different iteration space. So let's say we have a subrange, in this case, rows in a matrix, and we apply standard copy on it. We would expect it to work, and it would. This is exactly what you can do. What about now? So you still use standard copy, and you change the distribution underneath. It would also, disregarding the actual distribution scheme, it would always have to return the same result. It would always look like this. And this is exactly what you can do. So you can use standard copy. It would take forever, because it is element-wise copying. And you can use a dash copy, which would also have exactly the same result, but exploit the interaction with the pattern types and views to employ an optimized blocking communication scheme instead of an element-wise copying. So this is what you get every time. The canonical semantics are always the same. Underneath, we have the algorithms have to adapt to the local storage. So this is where the mappings between those index sets come into play, because that's exactly what algorithms have to do all the time in our case. They always have to map the pre-existing local iteration order and map it to a canonical index set, and it would return exactly the same result in every case. So all of those would always get the same result and always be optimal. Okay, now we have subranges in a one-dimensional distribution. How about a two-dimensional one? We already see that the index set gets a bit messy. So you can also read it as slice. Sub is just more generic. So, sub is for a subset or a subrange. Slice wouldn't work for a subset, so that's why we use sub. It's also a bit shorter. So the template parameter is the dimension. First dimension is rows. So we take rows 2 to 4 exclusive, and columns 2 to 7, and this is the rectangle you get. And when we translate this to the local index space, it would look like this. So sometimes it is contiguous range in local memory, sometimes it is not. It is not trivial to write a formula by hand that would resolve whether an index range from an operation like that would be contiguous at a specific unit. Because when we did, we had a solution for that without views, and it was similarly complex like the early one-dimensional example, so it was pretty horrible. And the actual motivation for what we do. So let me show you some matrix views. So it's the same kind of visualization we had before. Let's say matrix subviews, that would work. That is our matrix. I will just duplicate it to the top so we have it always in view. It's just maybe Oh, I forgot to pipe it, sorry. There you go. So that's our matrix. We take a subrange of that. So this is pretty much the example you saw on the slide. And it starts here and ends right there. It's of course not highlighting it here. Just a second. It starts here and ends there. So what's interesting about that? The white number to the very left. Whoops, here we go. Here we go. Sorry. The white number to the very left is the global index. So when you take the subrange of that, the global index is still preserved. When you call index, so pipe index on the subrange, you get a multidimensional index set and would reflect the original global index. And you can take blocks from the subranges and just use a dash is contiguous, dash is locally at, etc. to determine whether this specific block from that subrange is local to a specific unit and contiguous. So why do we need contiguous? Well, if it's not contiguous, we would have to pack it, for example, for the hello exchange we had before. So let's I have this up here so you can compare if it's right. You see those numbers. So we know we are at this one. Still, everything is contiguous. Oops, now I started. So 9 and 11. This one, where is it? 9 and 11. Here we go. This one is not divided. Not contiguous. And it's really hard to find that out by hand. So in this case, I can show you the code. This is the Submatrix view example. And of course, you can also view it on GitHub. Link will be in the slides later. So this is what we do. This is the fully specified declaration of a matrix. Users actually don't use the this overly verbose variant. So I take submatrix. I take blocks from that and indices. And then I just ask the block whether it is divided or not. So is locally at my ID, that is to say it's a local block, or it's divided. If yes, I have to compact it. If not, I can just use standard copy for the whole range. And you get that for every block in this thing. And you can get, so in the beginning we had the example of halos. So can it actually do halos? Let's take this example. I take a block, so I can specify a block by its block index. So the first block in every column and rows. So this would be this one. Then, Then I expand the block. Expand takes relative values. So it will be renamed to expand by or stretch by, because otherwise the API would be a bit inconsistent. So in the first, I expand this block in the first dimension by -1, that is one row up, and the second dimension to the left and to the right, I expand it by 1. Then I shift it to the right, and then I take the intersect to block 5. So this is an actual example that we really need from application code. And there was a grad student, a really talented one. I can show you the chat transcript after the talk. It's you will see why he was lucky to have this pull request. So let's see if what we can do with halos. I think I used 4, I'm not too sure. Those examples also take parameters, so command line parameters, to play around with it. So this one is called halo views. Yeah, this works. Okay. So this is our matrix. Forgot to pipe it again, sorry. So we take from this, we take the first block. So this is offset and extends. Offset 0, 0, it's the first block, extends 2, 2. We expand it by 1 in every dimension, but it doesn't expand to top and left. Why? Because there is no, the index basis ends there. I don't know when you ever had to calculate index those halo cells by hand. Just one of the most common mistakes is to disregard that you do not have, say, a torus distribution. This would lead to nice effects. But in this case, you can't do anything wrong. You just yep.
Do you support a torus in those cases where
yes, in this branch, not yet. But I used to support it, and it will be supported again to avoid the nasty word bug. But yes, of course we do. And also irregular distributions, and there's a whole unknown chapter on sparse distributions. Okay, then we do that for every block, and now we shift it, and of course we shift to the left. I will show the original matrix to the top and top. So we take. I will not demonstrate every block, but you will soon see that it works. So that's the first block. It's this one. We expand it, so we get this range, and now we shift it to the right, and we get this range here. And as you see, it now, where is it? Yeah, it still preserves the global index range. You still get 1, 2, 3, 7, 8, 9, etc. So should you ever need it, because in the code I never use the index set at all. Use index set algebra to work, and you can just ask them for the index that they just happen to use. But you don't, as a user, you usually don't have to use to actually read those indices. They're just there. And the next one. And as you can see, it works pretty nicely. Oh, now we have some real ones, some internal blocks. Now this is an internal block. And as you can see, this is a pretty complex view chain. So it's matrix, block 5, expand in both dimensions, shift it, take the first block. And I don't have the assembly right here, but I can show you after the talk. It is really compact. So there's not much copying going on. It's pretty much all moved away and const expressed away. So as you can see, so combined with what I showed you earlier, so that you could actually ask the blocks like block is strided, block is local, block local add, etc. This makes Halo exchange really trivial. So now the simple task. So it is simple to draw on paper. This Halo exchange. It actually is just as simple in code. I'll just show you the implementation of this Halo example, and that will conclude my talk. So, here we go. Oh yeah, just one disclaimer. All I do runs on this branch, feed, to the very bottom right, feed 192 and use. It is not merged into development yet. I will try to get to it on the weekend. So here's the code I just demonstrated. It's pretty much what I explained before. So here's the expand. Oh, we have the block first somewhere. Where's the block? Matrix blocks. Here we go. So you can use this style. You can use dash blocks matrix, or the pipe style, which is matrix pipe dash blocks. And if you know that you need a specific block, you can also say block, 0, or block, I don't know, 2.3. So when you pass it an array, it's interpreted as coordinates. In this case, we want all of them. And this is a general rule in the API. When there is an operation that is in plural, like blocks or chunks, strides, there also is a singular variant that just takes the index. Okay. What's it complaining? Oh, sorry. Okay. So we take the blocks. From the blocks, I want the index because that's what I print here. There, I have the block index somewhere. Yeah, here to the to the very left. I can't see my mouse, but here we go. So this block is corresponds to block 6 in the global index range. So that's where I take the index from. I want the offsets. That's where I print them. I expand it in every dimension. I want the offset instance of the header block. Shift it. And take the first block of that. So it's only looking a bit lengthy because of all these print statements and step statements in between, but actually you can just write it in one line, of course. There we go. Okay. Yes, and that concludes my talk. And I hope I get a lot of nasty constructive questions. Yes?
I have a few of those. Do you have a Z order partitioning? So
Oh yes, you do modern order. Yeah, of course. Yeah. Space filling. We have lots of space filling curves. Those are not in the official development branch because we have some grad students working on them on the master's thesis. But yes, we do. And speaking of NVIDIA, we also have a CUDA backend for that.
Yeah, this is me asking as somebody who used to be tangentially involved in UPC.
Yeah, there is a reason why I put, so at the very beginning, I called them the Finno-Ugrian Esperanto speakers, that is pretty much the GPUs. And we have a backend, so we have a Dart. Dart is for dash runtime, it's written in plain C. And it's pretty much just to decouple from the communication backend. There is one in CUDA. But I didn't test the view expressions integrations for CUDA. So that's, yeah, it's on my to-do.
What communication backend is Dash built on top of? So is it just on
So
top?
actually, so we have in the canonical one is MPI. We use one-sided MPI. But of course, there's good reason to also support GasNet, and we have a nearly complete implementation in GasP. So those GasP, this is for global address space programming interface, and GasNet is for global address space network, which is to say those are communication backends that are specifically designed for this one-sided access, so RDMA, so to say. MPI has RDMA since MPI 3, right? And it has its issues. Well, not according to the standard. MPI implementations have issues with progress communication, but it's not in the standard. So it's, in this respect, the standard doesn't have a problem.
So that's sort of leads to my next question. So you showed one asynchronous API, which was something like style API used to compare. Do you have a more of a handle-based API feature?
Of course, we have every Dash algorithm also has an async variant, and it uses so on the C++ side it's a Dash future, and below, of course, it's an MPI handle, rget, whatever you have, yeah.
So then, does Dash spin up its own threads for progress, or does it have some sort of privacy?
We have several approaches for that, and they can be configured at compile time in several places, at runtime in several places, because it is just not that trivial. But that's not exactly our fault. It's a problem everyone has that uses MPI 3. Progress just is a problem. And we have an own paper. It's 2 years old now, where we employ the MBAR-pitch variant. That is to say, you have one watchdog thread, and yeah. And what we achieved is we made it more efficient than the official MBAR-pitch flag, at least on the machines we could test it. Not because we are geniuses, but just because the official implementations of that were suboptimal.
How does your performance compare to UPC++?
I have to say that I did not pay you to ask this question. We are not ashamed. That is to say, we are measurably better. So measurably doesn't actually mean significantly, and we also, of course, only tested on, I think, 4 supercomputers, and any pull request in UPC++ or Dash could change that, but I would say we are on par with some backup systems. And there is, of course, papers for that, so on the last slide, depending on what you're most interested in. well, there's my NASCAR jacket. And also some links. So of course there's project.org, that is the official URL of the DFG research project. More interesting for you, github.com/project. This is where the implementation of Dash and everything I showed you right now is, and also the heat equation that just refused to play in the beginning. And of course we have a Slack channel. And in the Dash wiki, which is doc.dash project, we have paper slides, wallpapers, and whatever you can find with the search function. But in the paper section, there's also the paper I mentioned. And there's a dated paper, so it's from last year, on the Dash matrix. And I would like to say, just to pin the recent advancements in views to this publication, because the API that we propose there does not use free functions. So you have matrix.local.sub as opposed to sub of, matrix of, etc. And there is a nice talk that is taking place exactly at this moment by Klaus Igelsberger, which is called Free Your Functions, and I wholeheartedly support his statements. Yep.
Are there any applications you'd like to highlight that are using Dash in production?
Applications that use Dash in production. Well, it depends on what you mean by production. But we do not have a reference.
Scale?
Oh, large applications, we have lots of those. We have, of course, the standard reference benchmarks like Lulash, NASPB, etc. And we run those on a whole island of Supermook and Cray and Hazelhan and Cori and whatnot. So it is well tested and behaves reasonably in large scale. But we do not have a reference implementation like, for example, Cocos had.
Well, I guess I mean like applications that are using this that didn't bring it in as part of Dash development, right? I mean, do you have like actual users?
Or like the one
like
in the beginning.
Independent of this project.
Like the heat dissipation example in the beginning. Yeah, we used to have a cooperation, but unfortunately their funding ended. We have a specific part in the DFG research team that is only occupied with application development, and they are doing molecular dynamics. But they are affiliated with the Dash project. So what you are asking for is pretty much the freelance
Dash experts bring this into their application. I guess I'm looking for.
There is a user base that is really active also on Slack. You should join just now. There is an active user base and also an active support, so that's not the problem. But we do not have a reference application like Cocos has, for example. Yes.
So in here, you take a rectangle and like move it around.
Yes.
And it has like these local indexes. And what I'm interested in is like if you have the half of the matrix is your interest, like diagonally, cut the matrix diagonally, and only have the top region. So, and I want to iterate this top region of all.
So the question is, what if you do not want a rectangular subregion of the matrix, but a triangular one?
Yeah, like yes.
This is actually easy. Once you have the operations that are already there, there is no triangular, built-in operation for triangular subregions, but it's pretty easy to implement because you just need the sub expression and then just subtract one dimension in every step until you reach 0. So no, there is no built-in expression for triangular subsections, but it's rather easy to implement. Actually, I can show you outside that.
Okay.
Yeah.
Have you done any work with sparse data?
Yes, we do, but it's not there yet. The problem is so for sparse data we use cell C sigma, which is pretty much a generalization of sparse memory storage. Cell C sigma. So it's cell like the cells C, and then sigma like the Greek letter. I know I didn't pick the name. Speaking of naming, I'm really sorry for the camel case containers. Not my choice. So the reasoning was, well, there are so many people that would use, say, using namespace dash, using namespace did or something. Or so when you have an array or vector, because you stick to STL semantics, so it would even compile, it would run, and you would use a dash vector instead of a std vector and wouldn't even notice. And so we use camel casing for containers. But apparently, this isn't a problem for algorithms, because those are lowercase. So I didn't pick it. You can download a header that just contains type aliases. That's one I actually use, and yeah.
I'm sorry, would you spell that again? You said use something called cell C sigma.
Cell C sigma, exactly. I can write it down, or I can just give you the paper. I can just hack it into the console. So it's cell C and then sigma, like the Greek letter sigma. This is, I think it's from Harker and Bella.
I bring that up because it seems like, in a way, you can think about it as an indexing manipulation as well.
Of course, yes, of course. That's also what
The real data layout is physical, and then the way that it's treated by the.
I mentioned it briefly under my breath when I explained the pattern concept, which is here. Here we go. And you see that to the right there is a diagonal imbalance, and the only reason you need diagonal, or typical reason you need diagonal, is because you have sparse data. And for that, you wouldn't use a regular decomposition, but an irregular one. So you have a k-diagonal, and the more the higher the k, the bigger the region gets.
So you just store the diagonal in that case.
That's one way to do it, yes. So there's an own paper on that, this from the Cell C Sigma authors, and that's our approach. But views don't support it just yet. So as you see, the API still isn't perfectly stable. We have things like expand that expect a relative offset that should actually be named expand by and stuff like that. But we are getting there, and we have a meeting in 2 weeks where the whole Dash team comes together and fixes the API. Okay, no more questions? Then thank you very much.